Hello, Matt here from ChemistryStudent.com. In this video, we're going to look at the terms equivalence point and endpoint for acid-base titrations. We're going to talk about the difference between equivalence point, endpoint, and neutralization point, and look at how to choose an indicator for an acid-base titration. The theory and method behind acid-base titrations has been covered in a separate video. Check the links in the description below. Before we talk in detail about equivalence points and endpoints, it is essential you are comfortable with the idea behind an acid-base titration and acid-base theory. According to the Bronsted-Lowry definition, acids are proton donors and bases are proton acceptors. Alkaline solutions are formed when a base dissolves in water and hydroxide ion concentration becomes greater than H+ ion concentration. When an alkaline and acidic solution react together, a neutralization reaction occurs and a salt and water are produced. A titration is a practical technique that can be used to find the concentration of a solution of an acid or base. An acid or base solution with a known concentration is added from a burette to a base or acid solution with an unknown concentration in a conical flask. An indicator changes colour when the pH of the solution suddenly changes, and we use the volume of acid or base added at this point to find the concentration of the solution initially in the flask. pH is a scale used to represent how acidic or alkaline a solution is based on the concentration of H+ ions in it. A solution with a pH of 7 is considered neutral at 298 Kelvin, and a solution with a pH lower than 7 is described as acidic. The lower the pH, the more acidic the solution and the higher its H+ ion concentration. A solution with a pH above 7 is considered alkaline, and there is a higher concentration of hydroxide ions than H+ ions. The higher the pH value, the higher the concentration of hydroxide ions, and the more alkaline it is. Recap done? Let's go! During a titration, the pH of the solution in the conical flask or beaker will change. As a base is added to an acid, for example, the pH of the solution will increase. If we actually measure and plot a graph to show how the pH changes, we get an interesting shape called a pH curve. For example, if sodium hydroxide, a strong base, is added to hydrochloric acid, a strong acid, the curve looks like this. If you track how the pH changes, there is a sudden, rapid change where the solution appears to almost go straight from acidic to alkaline. It is this rapidly changing part of the pH curve that we are really interested in with a titration. It is at this point that the solution is switching from acid to alkali. In other words, it is during this moment that all the acid molecules that were in the flask at the start have reacted with added hydroxide ions. There are no acid molecules left to react, and any more hydroxide ions being added just make the solution alkaline. The exact point at which there is no more acid left and no excess base or hydroxide ions present is called the equivalence point. At this point in the titration, there should only be salt and water present. Just enough base has been added to perfectly react with all the acid present at the start. Any extra base added after this has nothing to react with and causes the pH of the solution to rapidly change. This equivalence point will occur very suddenly in a titration. It's a bit like imagining a seesaw with the moles of acid and base on each end, with one constantly being added to. At some point, the seesaw will start to tip, and bang, it will suddenly pivot over completely. During this pivoting, however, there will be a very short moment in time where the amount of acid or base added to one end equals the amount of base or acid on the other end, and the seesaw will be level. Although you can't really see this exact moment unless you watch everything in slow motion. However, you know it happens in the middle of the seesaw tipping over. This pivoting is like the sharp line of a pH curve, and the equivalence point in a titration, the moment at which the seesaw is level and the amount of acid or base added is the same as the amount needed to completely react with the base or acid in the flask at the start, meaning none of each is left over. The exact equivalence point will be in the middle of the sharp line in a pH curve, just like the moment the seesaw was level whilst it was in the middle of tipping over. In a titration, we can't see when this is happening, and instead try and identify this point by using an indicator. When the indicator changes colour and we stop the titration, we describe it as the end point. An indicator will change colour at a specific pH. We want the indicator to change colour at the same time as the equivalence point is reached, meaning we want the endpoint and equivalence point in a titration to occur at the same time. We've seen for hydrochloric acid and sodium hydroxide that the equivalence point occurs in the vertical section of the pH curve as the pH is changing rapidly. As long as the indicator changes colour at any pH in this vertical section, the volume of sodium hydroxide added to reach the endpoint and equivalence point should be the same. For example, the indicator phenolpthalein changes colour at approximately pH 8.5. Below 8.5 it is colourless. Above this it is a red-purple pinkish colour. If we were to use this indicator in a titration then, the endpoint of the titration would be when the pH of the solution gets to around 8.5, as this is when the indicator would change colour. We can see in this pH curve that the equivalence point, the point when all acid is reacted and no acid or base is present, and the endpoint would overlap. The endpoint and equivalence point would occur at the same time in the titration. Great! This means when the colour changes, the endpoint, we know it also represents the equivalence point, and the solution in the flask contains only salt and water. It is really important to understand, however, that the endpoint and equivalence point are separate and not connected. We just want them both to occur at the same time in a titration. For example, if we were to use a different indicator here, such as methyl violet that changes colour at around pH 1.5, everything would be wrong. The colour of the indicator would change at around pH 1.5, meaning the person carrying out the titration would stop the titration, the endpoint, way before all the hydrochloric acid has been reacted or used up, and the equivalence point is nowhere near reached. This is why we have to be careful when selecting the right indicator for a given titration. This is especially true when carrying out a titration using weak acids or bases. This can be seen in more detail with a video on pH curves. Check the links in the description below. We want to choose an indicator that will change pH somewhere in that vertical section in a pH curve, because we know that the equivalence point is also in this region, meaning a colour change, endpoint, can be used to represent the equivalence point. One massive source of confusion for students at this level is the idea of a neutralization point. A solution at 298 Kelvin is considered neutral if its pH is 7. Therefore, the neutralization point in a titration is the point at which enough acid or base has been added to get the solution to a pH of exactly 7. Simple as that. It has absolutely no connection to equivalence point or endpoint. The reason things can get confusing is that for a strong acid and strong base titration, like the one here with hydrochloric acid and sodium hydroxide, at the equivalence point the solution will be neutral and have a pH of 7, as the solution formed will only contain sodium chloride and water, meaning the volume of base added for the neutralization point and the volume of base added for the equivalence point are the same. It takes the same amount of sodium hydroxide to reach the equivalence point as it does to make the solution pH 7. This doesn't have to be the case though. If, for example, hydrochloric acid and ammonia were being titrated instead, things get a bit different. If ammonia, a weak base, is added to hydrochloric acid, ammonium chloride is formed. At the equivalence point, enough ammonia has been added to perfectly react with all the hydrochloric acid molecules present at the start. The concentration of HCl and NH3 in the solution should be 0. Makes sense. The thing is, a solution of ammonium chloride doesn't have a pH of 7, meaning when the equivalence point is reached, the solution isn't pH 7 and therefore isn't neutral. This is because ammonium ions are a conjugate acid of the base ammonia. They will form their own equilibrium system in the solution, and some will dissociate back into ammonia and H+ ions. This means although there is no HCl left from the start, there are still H+ ions in the solution, and this means the pH of the solution will be slightly less than 7. To get the solution up to pH 7 and make it perfectly neutral, a little bit more ammonia will need to be added. Now, however, more ammonia has been added than was needed to react with the starting HCl molecules, and this new volume, the neutralization point, isn't the same as the equivalence point. This is why the term neutralization point can be a bit tricky for students, and if possible should be avoided. Try just to refer to equivalence points and endpoints if possible. So, to summarize, pH curves for titrations show how the pH of an acidic or basic solution changes as a base or acid is added to it. A sharp change in pH occurs as the solution changes from acidic to alkaline. It is this sharp change that enables an indicator to be used to show when a titration should be stopped. Equivalence point refers to the point in a titration when just enough base or acid has been added to react with all acid or base molecules in the starting solution, and there are no leftover amounts of either acid or base in the solution. Endpoint refers to the point in the titration when just enough base or acid has been added to cause the indicator in the solution to permanently change colour and the titration gets stopped. When carrying out a titration, the equivalence point and endpoint should be as close together as possible. They are, however, completely different things. Different indicators change colours at different pHs, and different indicators need to be used depending on the acid and base being used in a titration. Neutralization point refers to the point in a titration when the pH of the solution becomes exactly 7, and the concentration of H+ and OH- ions are the same. This isn't always the same as the equivalence point in a titration. The molecules of a weak base can accept H+ ions and form a conjugate acid. This conjugate acid can then form its own equilibrium in the solution and partially dissociate, releasing H+ ions. This means the point at which the amount of acid and base cancel each other out, the equivalence point, wouldn't be pH 7, as the conjugate acid form still releases H+ ions. To get to pH 7, more base would need to be added than is needed to perfectly react with all the acid originally present, meaning the neutralization point would be past the equivalence point. I hope you found this video useful. Please check out other relevant videos in the links given in the description below, and visit chemistrystudent.com for free notes and revision materials.